I will quickly go through what I have covered in the last class as a prelude to establishing the different analogies between heat, mass and momentum transfer. So, we started with the conservation equations, non-dimensionalized those conservation equations using standard non-dimensionalizing parameters, and there we saw that the form of the equation are slowly coming to mimic one another, and more importantly the emergence of dimensionless groups out of the non-dimensionalizing process is automatic. So, what you are going to see is you would be able to identify the dimensionless similarity parameters which are going to be relevant in each of these cases. So, we saw that Reynolds number is going to be important in the case of momentum transfer, both Reynolds and Prandtl number in the case of heat transfer, and Reynolds and Schmidt number in the case of mass transfer. So, we wrote those equations, and we also wrote what are the boundary conditions which can be used to solve this specific process, and we have divided the boundary conditions into two different type of categories. One is what is going to happen at the free stream and what is going to happen at the intersection, at the interface between the liquid and the solid surface. So, one set of boundary conditions for on the solid surface, the other is in the free stream, and we would we have written the similarity parameters for each of these processes. So, this is what we have seen starting with the conservation equation, which is the momentum transfer, the Navier-Stokes equation, the x component of Navier-Stokes equation written for flow inside the boundary layer. So, utilizing all the assumptions and approximations, the boundary layer approximations that I have discussed before. And the circled one is the dimensionless parameter, similarity parameter, which is Reynolds number. The sets of boundary conditions at wall and free stream are no slip, and the velocity is equal. Velocity is going to be equal to u infinity by v, where u infinity is the velocity, is the free stream velocity at a given x location, and v is the approach velocity. For the case of flow over a flat plate, in absence of any dpdx, that is pressure gradient, u infinity would be equal to v. But in order to maintain the general nature of the boundary conditions, we have kept it in the form of u infinity by v. Now, we next took let us look at the energy equation, which again is same, that is the advection. These terms are on the left hand side, and the diffusion term is on the right hand side, and again the circled one would resolve into the product of Reynolds, the similarity parameter would be Reynolds number and Prandtl number. The conditions are, as since we have defined T star in this form. So, the value of the dimensionless temperature at any axial location on the solid plate, that is y equal to 0, would be 0, and the temperature at a point far from the solid plate would be equal to 1. Similarly, for mass transfer species balance equation, this is nothing but Reynolds and Schmidt number. The conditions are identical as this. So, these equations are more or less look like the same, except they have Reynolds number, or 1 by Reynolds number, 1 by Reynolds and Prandtl number, and 1 by Reynolds and Schmidt number. And if you look at the boundary conditions, they also look the same, except that in the case of flow over a solid surface hydrodynamic boundary layer, this dimensionless velocity at infinite distance, at a large distance from the solid plate, would simply be equal to u infinity by v. So, with this we proceeded with the functional form of the solution. We saw that the velocity is going to be a function f1 of x, y, Reynolds number and dpdx, and the shear stress is velocity gradient multiplied by mu at y equals 0, since I am specifying the value of y. So, and then non-dimensionalizing it. So, the form of Cf, the friction coefficient, by definition is tau s by half rho v square, and when you put this form of tau s in here, what you get is this is the form of the friction coefficient. and the friction coefficient would obviously be a function of x star. It will not be a function of y star, since a value of y, specific value of y is mentioned here. It is going to be a function of Reynolds number, but if you define the geometry, if you prescribe the geometry, then dp star dx star, the pressure gradient, can be obtained by through the use of, let us say, Bernoulli's equation in the inviscid flow region outside of the boundary layer, and p is a function, p is not a function of y. So, therefore, the pressure difference between these 2 points outside of the boundary layer, that can be solved, that can be evaluated through the use of inviscid flow theory, would be equal to the pressure difference between the 2 points inside the boundary layer, since p is not a function of y. So, Cf for a prescribed geometry is going to be a function of x star and Reynolds number. Similarly, we started with the energy equation, and we identified that T star is going to be all this, additional would be Prandtl number, and then we start with the equality of convection and conduction at the solid liquid interface, and therefore, from that we obtain the value expression for H, and finally, the expression for Nusselt number, which is the dimensionless pressure gradient at the wall, that means at y equals 0. Since I have specified the value of y, so Nusselt number would be a function. The functional form of Nusselt number should contain, which I call is at F4, x star, y star is specified, Reynolds number, Prandtl number, and if I specify the geometry, then dp dx would not appear in the functional form of the Nusselt number. So, this is what Nusselt number is, and if you find out an average value, that means length average value of Nusselt number. So, your x star would also not be there, since you are integrating this from 0 to x star, from 0 to L, the entire length of the surface. So, in that case, Nusselt number, average value of Nusselt number is simply going to be a function of Reynolds and Prandtl. Exactly the same way, I define what is HML by DAB, that is Sherwood number, starting with the functional form of CS star, the same way as in heat transfer, where HM is the convective mass transfer coefficient. So, this is Sherwood number is by definition then is the dimensionless concentration gradient at the interface. Therefore, for a prescribed geometry, Sherwood number would simply be, I call this function as F7, which we still do not know, but the F7 should contain x star, y star would not be there, it is Reynolds number and Schmidt number. And same as in the case of average value of Nusselt number, if I find out what is the average value of Sherwood number, that means if I integrate over the entire length and denote the convective mass transfer coefficient as h bar m, unlike this HM. So, h bar m by DAB, which is the average Sherwood number, it would be a function of Reynolds and Schmidt. So, just to show these two together, here you can see that the form of Nusselt number F5 and F8, in one case it is Reynolds and Prandtl, in the other case it is Reynolds and Schmidt. And if you compare that with CF, the friction coefficient, or rather CF REL by 2, this would simply be equals F2 x star REL. Okay. So, these three F2, F4 and F5, F2, F5 and F8 together would give you some idea about how we can try to get a relationship between all these things. If I concentrate on, let us say, F1 and F3, I think it is visible. So, F1, what I have in here is the functional form of velocity, F3 is the functional form of temperature, and similarly I have an F6 in here, which is the functional form of the dimensionless concentration. Now, let us go back to this equation, this case again, before we go into Reynolds analogy. I have these as conservation equations. in this I have 1 by Reynolds times Prandtl. In here I have 1 by Reynolds times Schmidt. So, this is nothing but 1 by Reynolds times Prandtl number. This is 1 by Reynolds times Schmidt number. So, forgetting about this part, if I only consider these three cases, then I can say that these three equations will be similar only when the Prandtl number is equal to 1 and Schmidt number is equal to 1, and for the case where dp dx is 0, that means we are dealing with a flat plate. So, think about the implication of our assumption of our statement here. I would like to make these three equations same, identical. All are going to have an advection term on the left and a diffusion term on the right. And when I can say that these three equations are equivalent only when dp dx is 0, because you do not have any dp dx in these two equations. So, dp dx has to be 0, and dp dx to be 0 signifies that the flow is taking over a flat plate. And you see this the other terms which are there. The first equation, momentum equation, contains 1 by Reynolds number. The energy equation contains 1 by Reynolds number times Prandtl number, and the third equation, species balance equation, contains 1 by Reynolds number into Schmidt number. So, in order for these three equations to become identical, the additional constraint that one has to put is that Schmidt number is equal to 1 and Prandtl number is equal to 1. So, only in that very restrictive condition where Prandtl number of the fluid which is flowing, having momentum, heat and mass transfer, its value should be equal to 1 and Schmidt number should be equal to 1, and the flow is going to take place over a flat plate such that the pressure gradient dp star dx star is equal to 0. When these conditions are met, the momentum transfer equation, the energy transport equation and the species transport equation all will look identical. So, in addition, if we can show that the boundary conditions are also identical, then these three systems, one having heat transfer, the other having momentum transfer and the other one having mass transfer, these can be expressed in terms of same expressions. That is what analogy is all about, such that the expression, if it can be obtained by experimental or other means for one type of transport process, I should be able to use it for the other transport process by simply making certain obvious substitutions. So, once again, these three equations are now identical since I have assumed dp dx to be 0, the Prandtl number is equal to 1 and the Schmidt number is equal to 1. Now, let us look at what happens to the boundary conditions. U star 0, T star 0, C star 0. So, at the wall the three boundary conditions are identical. At the free stream, C star is equal to 1, T star is equal to 1. However, U star, which was equal to U infinity by V, now would be equal to 1 since I have assumed dp dx to be 1, and dp dx to be 1 essentially is a case of flow over a flat plate, and we understand for flow over a flat plate the value of the approach velocity would be equal to the value of the free stream velocity. So, by making the assumption dp star dx to be equal to 1, what I am doing over here is that I am making all the boundary conditions identical both at the wall as well as the free stream. So, this would give us the first type of analogy that we are going to get, but once again when the equations are same and the boundary conditions are same, then all these three systems would be called dynamically similar. So, if these three governing equations are dynamically similar, then it it allows us to use the correlation for one as the correlation for second and for the third, and provided we simply use the right kind of variables for which are specific to the heat transfer, mass transfer or momentum transfer process. So, the analogy, the most restrictive form of analogy that one can choose is for the case where the flow is taking over a flat plate, it is a laminar flow, and the value of the dimensionless similarity parameters, namely Prandtl number and Schmidt number, are equal to 1. This analogy is called the Reynolds analogy, and as I mentioned, it's the most restrictive analogy form of the analogy between heat, mass and momentum transfer. So, we would start first with the Reynolds analogy, which simply tells you that it is going to be valid when dp star by dx star is equal to 0 and Prandtl number is equal to Schmidt number is equal to 1, and then the conservation equations are all of the same form. So, this would give you conservation equations same, boundary conditions same. So, solutions of u star, t star and cs star, the dependent variables must be equivalent. So, this is what analogy is, and if you look at your class notes, the u star is essentially expressed in terms of function f1, t star was expressed as f3 and cs star was expressed in terms of f6. So, f1 must be equal to f3 and is equal to going to be f6. So, since the solutions of these are equivalent, same is true for Cf, the friction coefficient, Nusselt number and Sherwood number. So, what are the coefficients for friction? So, Cf is Cf times REL by 2 is F2, Sherwood number is equal to Sherwood number is equal to F7 and Nusselt number I think is going to be equal to F4. So, these are going to be the same. So, therefore, F2 would be same as F4 as same as F7. So, Cf times Re by, so F2 is nothing but, if you again see the definition of F2 is Cf REL by 2, F7 is Sherwood number and F4 is Nusselt number. So, if F2, F4 and F7 are equal, which tells you that Cf REL by 2 is equal to Nusselt number is equal to Sherwood number. So, this is the relation that you would get in the case of Reynolds analogy. Sometimes this analogy is slightly modified, that is, it is expressed as Cf by 2 equals Nusselt by Reynolds equals Sherwood by Reynolds REL, and since we understand that PR is equal to SC is equal to 1, therefore, nothing the generality of the solution, generality of the expression would not be disturbed if I bring in these two terms here as well. So, initially from here what you get is Cf by 2 equals Nu by REL and Sherwood by REL, but you just bring in these additional numbers, knowing fully well that in order to have Reynolds analogy, I have assumed Prandtl is equal to Schmidt number and its numerical value is equal to 1. So, therefore, have expressing CF in terms of Nusselt Reynolds Prandtl or Sherwood Reynolds Schmidt would not change this, the generality of this, and this Nusselt by Reynolds times Prandtl, this is called the Stanton number, and Sherwood Reynolds Schmidt is again also called Stanton number. And this is either called Stanton number for mass transfer. So, this is Stanton number for heat transfer and this is Stanton number for mass transfer. These are just definitions. So, a more generalized and modified form of Reynolds analogy is written as Cf by 2 is equal to Stanton number based on heat is equal to Stanton number based on mass. So, this is the form of Reynolds analogy that can be used when you have this condition dp dx to be equal to 0, Prandtl number is equal to 1 and Schmidt number is equal to 1. So, this analogy relates the key engineering parameters of velocity, thermal and concentration boundary layer. So, the significance of this simply relation is enormous. It tells you now that the engineering important parameter, for example, the friction factor in the case of momentum transfer, the heat transfer coefficient, convective heat transfer coefficient and therefore Nusselt number in the case of heat transfer, and convective mass transfer coefficient or its dimensionless form in Sherwood number, they all can be expressed, they all are related by simple equality sign. So, therefore, if, and we know that we have expressions for CF in laminar flow, expressions for CF in turbulent flow. We have some idea of what is going to be the expression of heat transfer in laminar flow, but we have not studied heat transfer in turbulent flow inside the boundary layer or mass transfer in turbulent flow inside the boundary layer, and we do not need to, because with this analogy available to me and with our knowledge of the exact expression for CF in turbulent flow as well as in laminar flow, and if I use this analogy, what you see here is Cf by 2 is simply equal to Stanton number based on heat or heat transfer Stanton number. So, an expression for Cf in turbulent flow is available. So, with this analogy, then I should be able to obtain an expression for Nusselt number, or for that matter an expression for Sherwood number for the case of turbulent flow using a simple analogy which is known as Reynolds analogy. So, the hydrodynamic boundary layer is well researched, it is comparatively easier to analyze, since as I said before, the heat transfer and the mass transfer are coupled to the hydrodynamic boundary layer, but the hydrodynamic boundary layer, solution of the hydrodynamic boundary layer, the equation of the hydrodynamic boundary layer is not coupled with the temperature or with the concentration as long as the properties remain constant. So, which would be even more clear if you look at this expression once again. Here I have the velocity, but nowhere in this expression either the temperature or the concentration appear. On the other hand, if you look at the thermal boundary layer equation or the species boundary layer equation, you have the presence of U in both cases. So, in that way this momentum transfer can be solved independent to the solution of the thermal boundary layer or the species boundary layer. So, that is the reason why that this has been explored in greater details, both for the case of laminar flow, as we have seen in the case of Blasius solution, and the case of the turbulent flow, in which we have used 1/7 power law, the Blasius correlation, and so many other things, which gave us a comprehensive idea of the variation of the engineering parameter, which is friction coefficient, for the case of laminar as well as turbulent flow. But we do not have that luxury in the case of heat transfer boundary layer or species boundary layer. They are more complicated because of the appearance of U and V in here. So, a simultaneous solution of these two are needed, but we do not have to do that anymore, since we have the Reynolds analogy, which directly relates Nusselt number with the expression of the friction coefficient, either in laminar flow or in turbulent flow. So, an expression for Nusselt number can thus be obtained from the expression of Cf in the various types of flow. So, that is a big advantage, but let us think about the disadvantage now. What is the disadvantage? The conditions which I had to specify in order to obtain this Reynolds analogy is extremely strict, it is unrealistic, because it is unlikely that you are going to get a liquid whose Prandtl number is equal to 1, or whose Schmidt number is, and its Schmidt number is also equal to 1. That is a very restrictive, unrealistic boundary condition to have. So, what is the solution? I mean, you may have dP dx to be equal to 0 if it is a flow over a flat plate, and in the case of turbulent flow, the pressure drop, it does not depend on does not depend that much on the shape of the surface over which the flow is taking place. So, dP dx to be equal to 0 is also approximately valid for the case of turbulent flow. So, we need not worry too much about dP dx to be 0 or non-zero, especially for the case of turbulent flow, but we have to think about the value of Prandtl and Schmidt number, which are not going to be equal to 1, and it can have various values. For example, the Prandtl number for air is about 0.7, and there is a significantly large range over which the Prandtl number and Schmidt number of commonly encountered fluids can be. So, these two numbers can lie over a significantly wide range for most of the common fluids that we encounter, and therefore, a correction to the Reynolds analogy must be provided, which would allow the extension of this analogy for real fluids. That is done through the use of extensive experiments, and with an empirical approach. The new analogy, modified Reynolds analogy, has been proposed, which is now available over a large range of Prandtl and Schmidt number. So, that is what we are going to look at next, which is called the modified it is also called Chiltern both are same, the modified Reynolds analogy or Chiltern-Coburn analogy. What it would say that Cf by 2, it was Stanton number based on heat, which is only valid for Nusselt number equal to, for Prandtl number equal to 1, but the range of this can be extended if a Prandtl number correction is added to this relation, which is called, this is called JH, and it extends the Prandtl number from 0.6 to about 60. So, this is the Prandtl number correction factor added to Reynolds analogy to modify it for a wide range of Prandtl number, also known as Chiltern-Colburn analogy. And for the case of mass transfer, it is going to be Cf by 2 is equal to Stanton number based on mass and a Schmidt number correction factor exactly the same way as the case of Prandtl number is added, and this product is called Jm, and it extends the value of Schmidt number from 0.6 to 300. So, therefore, the modified Reynolds analogy or Chiltern-Colburn analogy, which is valid over a wide range of Prandtl number and Schmidt number, is expressed as Cf, the friction factor by 2 is equal to Stanton number times Prandtl number to the power 2/3 equals Stanton number based on mass Schmidt number to the power 2/3, or Cf by 2 is equal to Jh equal to Jm. So, this is the Chiltern-Colburn analogy, and J is called the Colburn J factor. So, this is the analogy which we are going to use for all our calculations in the subsequent exercises that we are going to see. So, this is an unique relation which connects all three transport processes together, and it gives a tremendous advantage to experimentalists, practicing engineers and so on, where one set of experiment which is possible. Let us say the situation is such that you can measure temperature, but you cannot measure concentration. Okay. So, on a prototype where the actual one is going to experience both heat and mass transfer, and you would like to know what would be the relations to be used, what are the design equations for that. You build a prototype, you do an experiment, but while doing the experiment, for some reason, let us say you see that it is possible to measure the temperature and therefore do the heat transfer experiment, but you cannot measure concentration. So, therefore, no mass transfer prototype experiment can be obtained with the system that you have right now. So, what you do is you perform the heat transfer experiments on the prototype, obtain a relation between, let us say, Nusselt number, Reynolds number, Prandtl number, whatever, from your experimental data. Now, what expression are you going to use for mass transfer? Since you cannot perform any mass transfer experiments, then you are simply going to use Chiltern-Colburn analogy. Make sure that the fluid that you are dealing with is having the Prandtl number and Schmidt number within the range specified for Chiltern-Colburn analogy, and simply write the expression, equivalent mass transfer expression of the heat transfer expression that you have obtained experimentally. So, it reduces your work significantly. It gives you a tool to predict the performance, the mass transfer performance of the device without even doing a single experiment on mass transfer. So, the utility of these analogies are extremely useful to all of us. So, whenever you think of an analogy, whenever you try to apply an analogy, always keep in mind what is the range of these parameters over which this analogy can safely be used. And if you are satisfied, then go ahead and use this analogy, and it would really give you the expression for heat transfer coefficient or mass transfer coefficient in turbulent flow without solving for the complicated boundary layer equations, governing equations that you have starting from the energy equation or starting from the species balance equation. So, what we will do in the next class is just will give you a brief few more ideas, fundamentals about the different thicknesses of the different layers, how they are related. For example, what is the thickness of the hydrodynamic boundary layer, the ratio of the hydrodynamic boundary layer and heat transfer boundary layer or mass transfer boundary layer, and so on. But after that, we are going to solve different problems, various problems which directly use the concept of analogy, and that would clarify your concepts even more.